probably here with Jean and Arun. So rather than talking about my personal relationship, I just want to follow up a little bit and share with you on how we are doing a lot of work in our group at CMU on real-time control, and just sort of share the vision of how we see the control, how is the control and operations going to change in light of having synchrophasors and real-time measurements. So this is our sort of staple figure that Shishing, who is sitting here, made some time ago. So it's basically, this is how we are thinking about the problem. It's in a mesh network. It is at a complex, high voltage network that we are doing most of the work. And you can think about this, in this case, it's just a 5-bus system, but it can be any interconnected network. And you have disturbances on the system. You have things that you can predict. We call these diamonds. You can put sensors, dynamic monitoring decision systems. You can put sensors, or you can put actuators at different locations. They communicate. And you basically online with this information close loops and balance this load as things change on the system. So to do this, and we heard this from Alstom, the first thing to do is basically to somehow align the output from the state estimation, to have a good state estimator and to feed state estimation accurate results to decision-making tools. So I'm not talking about analysis, I'm talking about decision-making tools and automation for closing the loop. So you can do many, many things. Here is a sort of the simple thing for steady state optimization, where you have state estimation feeding power system control, optimal power flow, and measurements. This was mentioned. They were in SCADA 2 seconds, now they're much faster. So this is how the problem is changing. Okay, so I will go through a sequence of things as much time as I have on several ideas that we are pursuing. One is, and Vahid said, is that we should think really about moving from preventive to corrective management, online management of the system. All pieces are there, and this saves quite a bit in terms of not having to have preventive reserves for the worst case contingencies and so forth. So one way to think about this, you are giving, this is what's being estimated, what's being predicted, the system load, and there are sort of two components that you see in the control center. One is the predictable component on 15 minutes scale, and then within 15 minutes there is a lot of stuff that you cannot predict, deviations in load, real reactive power load. And so the question is, can we use these online measurements to better do the scheduling for predictable component of load, and also have closed loop automation based on PMU, so that you actually don't have violations in frequency and voltage when you have hard to predict deviations in the system. So let me say just a few words on first why is it so important to have now better measurements for feeding basically ACOPF. A lot of people are working, there is a lot of ARPA-E funding on revisiting ACOPF, and I work outside of university on this also. The real bottleneck is bad data. The state estimator data, accuracy of state estimator is lower than the accuracy that you want to do with your optimization, so it sort of defeats the purpose. This is why these things are so intertwined. However, there is another thing that is going on, and a lot of work is happening also in terms of this predicted approach, model predictive approach to scheduling. So just to illustrate that very quickly, this is a sort of your traditional RPS system, and if you don't do predictions, you're basically going to have this, this is your system load, and the fastest power plant is going to have to follow it minute by minute. So you jerk plants, you go up and down, there is a lot of wear and tear. Instead of doing that, and Louis somewhere here, this was his PhD thesis, so you ask now, if I have a lot of input variations, predictable input variations, can you do model predictive scheduling with wind generation, for example? So observe the time scales. This is the slowest time scale, 15 minutes ahead of time. You're doing your model predictive optimization and predictions like 24 hours in the future. So what happens? a lot of interesting things can happen. So you want to replace some conventional power plants by wind power plants. And if you do it right, if you do these predictions, then this is your wind variations. But actually, when you do the dispatch, you will learn that it's optimal from the system level to store wind, not to use it all, and at the same time optimize fast, expensive gas power plants so that you don't need, let's say, capacity of new 8 gigawatts to follow the wind power plant. So this is a sort of basic gain that you would have if you predict and schedule in a model predictive way under uncertainties for predictable component. There is also something interesting that we learned. If you, instead of doing static dispatch, let's say for slow power plants that you cannot move fast, which are inexpensive, instead of turning them on and off in static dispatch way, you actually look ahead and you start ramping coal plants a little bit. So you're even using slow power plants better than you would use them with static dispatch. And this is all possible if you have real data to predict accurately things, let's say 15 minutes ahead of time for the next 24 hours. And the story goes, this is now where the smarts come in, how you integrate demand response and so forth. So JY is working, almost finished with her PhD thesis. You can also do the same thing with predictive loads participating. If they participate in, then what happens is if you have load that is elastic and participates in the same way as generation, you predict the wind and the demand responds in a predictive way rather than being elastic, and you don't have to have spikes in very fast power plants. Instead, they're very smooth. There's a lot of gain there. But I think the bottom line, and just one more example here, you can do the same thing with electric vehicles. Electric vehicles are basically adaptive loads, and everybody knows this curve. Then you would, if you do it in a predictive way, you don't have to have capacity that you would have when you did fast charging. So one more thing here to mention is the importance of the ACOPF, is that we have really not done much, at least in the US utilities, in terms of optimizing AVR set points, settings on grid equipment. And there have been a lot of studies which have shown that if you do the corrective way, at least for predictable contingencies, online, Vahid was talking about time is on your side. You have 1 hour from the first contingency. If you do this in corrective way and you do optimal voltage dispatches, you schedule a generation, you would save 20 to 25% total generation cost. This is huge. And this is just a little thing going back. I remember our reactive power distribution factors with Arun. We should actually very quickly, we have to use some of those analysis things to say, why is optimal voltage dispatch, helping? When I don't do voltage dispatch, I don't have that help. We have done some studies, and it's been co-authored with several industry folks, that exactly what Vahid was saying. If you had some trigger somewhere, you have contingency, and you monitor things, and you correct, let's say on 15 minutes basis, you actually would prevent blackouts, because you adjust as you go. It's not a split second thing. So on this close time scale, a lot can be done. Now, you remember, so that was for predictable component. What is more interesting, and where PMUs begin to make a very big difference, is PMU-based robust control on fast time scale. So what we have there, and Xixing is finishing his PhD thesis on stabilizing voltage control, stabilizing voltage in response to hard to predict deviations in reactive power, stabilizing flow deviations around the predictable ones on tie-line flows, using what amounts to sort of, I would still say, call it science fiction at this point, because we are not doing this with PMUs. You would have to use this system-wide, wide area measurement level, the same way as people are talking about wide area measurement special protection schemes, to decide what to measure, and from those measurements to which control to activate, let's say setting on ABRs, so that you compensate for the disturbance that you cannot predict. So the whole trick is here. You are very quickly going to get data saturation unless you decide what are the places to measure for control purposes. Okay, so just to say a little bit about GIM, this goes back to our pilot points. We did this in context not of PMUs, but if we have a given system, what is the best location to put the measurement so that you do this control? We are going to get there. This is automation. This is like AGC. Well, if you put it at this location, these are the deviations and voltage. It's outside of 5% allowable limit. If you monitor all loads and have no control, this is one point that I wanted to make. We cannot just monitor PMUs. We have to close the loops. Because here I'm monitoring and I have huge deviations. If I close the loop intelligently, then I have unpredicted disturbances, but I'm actually keeping the voltages within the limits. And that's the huge gain. This is like AGC now for ABC, and EDF has had it in the past. We haven't. Now if you have pilot point at different location, you'll get different performance. So going back to the work that Jim and I did on L1-based robust control for ABC, where do you put how many pilot points you have will critically determine if you are going to stay within acceptable limits or not. Okay. And the same thing, Shishing extended for automatic flow control. Now, I just want to put some breaks here. So when we go to the very fast time scale, we have done work with Jeff Chapman and Eric Allen, now who works at NERC, on split-second thing for transient stabilization. There, you have an example here where this is a split-second situation. Things are going to go out of synchronism. Voltages are going to collapse the last minute. And it is no longer clear that you can actually rely, in these cases, on fast communications or computing at the EMS level. So there is a very real danger that we may have going to complexity at a time scale where it's not feasible. So we have to address technical problems at various time scales to fundamentally different ways, using actually data that's manageable. So the major question that we are studying at CMU is what can be done in distributed way and what must have fast communications. This is a huge question. And again, it goes back to Caltech people are now routinely referring to the work on localized response that Jim and I did. It looks like if the network behaves like localized way, then you can do distributed control. Otherwise, you have to have communications. We have to look into that much more. So just to close, all these requires data. I cannot overemphasize. I've done control, but here, I think Yang Wang is here, this is his PhD thesis, is we are facing major things in actually having sufficiently accurate state estimator to support online scheduling, even on slow time scale. And here is the list of things that one has to worry about. And again, you have to do as much as you can in a distributed way in state estimation, find the right places now for finding the best, what we call information gain. And just to close, we still don't have a framework for thinking up, for designing this. We have PMUs, we have existing applications, we have state estimator, we have not linked. The link between the data that you need and the application still needs to be emphasized big way. So this is not understood at all by people who are pushing sustainability. They think the more you build in terms of capacity, the better you're off. Our job as the community is to show that with these smarts, what we call it just in time, just in place, and just in context, you actually can have some synergy between good hardware, good sensors, and the software so that you save quite a bit on the system. Thank you.